Slam. We always have a lot of fun with these. We put them off for a few years when we weren't meeting together, but this is exciting to me, so I'm looking forward to this too. If you're presenting, we're trying to have you self-monitor and keep yourself to, between 5 and 10 minutes or so. That's always a challenge. You got to be really prepared and know how to get the crux of the point you want to get off and not get onto tangents. And that's my challenge, I think, sometimes. But thanks so much for coming. And we will probably have a few activities during the summer. Scott generally has something going on with astronomy, looking at Jupiter or different planets and stars at sometime during the summer. And we'll put something out. If you don't get my emails that I try to send out only just before Science Sundays, let me know and I'll get you on the email list so you'll be aware of that, what's going on with those. And I was wondering, before we started, anybody see a good sighting of the Aurora Borealis? Yeah, not around here really too much. I know, Joanne, you and Scott went out way west and tried to get in the darkest spots and everything. You saw clouds. Wow, yeah. I know my daughter-in-law in Seattle sent some pictures that were just fantastic. And the thing that you can actually see is that out of a camera they come out better because you can delay for 3 seconds or something like that the aperture opening or the timing of the lens opening, and you get much more impressive results. So if anything comes out, try to take your iPhone out and change the setting, practice setting it for 3 seconds or 5 seconds. You get some amazing things. So, all right, this is always a lot of fun to get together and have people talk about things that are of interest to them, and I like to sit back and just hear, tidbits of fascinating things. So I thought, just kind of going randomly through here, I thought we'd get Scott talking about ergonomics. So if you should know that this thing can, if you have a PowerPoint, you can adjust it with that. You've done it before. So.
That's mine.
That's his.
That's mine, yep. Okay. Sorry. What you're seeing here is a software tool that can demonstrate or illustrate good body mechanics and bad body mechanics. The green lines are showing you good body mechanics. The orange or yellow or is so-so, and the red is positions that you try to avoid putting yourself into. Your body's got.
Do you want a portable mic?
I need my hands.
Oh, I see.
Your body's got certain natural curves. If you stand up and shake yourself out a little bit, you'll see that you got a natural curve in the shoulders, in the trunk of your body. You've got a natural curve in the lower back and a natural curve in the upper back. As long as you can maintain these natural curves, you're less likely to hurt yourself. If you're lifting, you want to squat down, get your hands around the object, and pick your chin up. Because if your chin is up, then it takes care of the natural curve in the back. You don't have to look at it once you've got it in your hands. You know where it is. So by picking your head up, you can help to maintain that natural curve. By squatting down, again, you're working to maintain that natural curve in your lower back. So that's basically a quick 2-minute, not even 5, 2-minute educational program on ergonomics.
Is that a special camera that?
No, I was taking with the phone.
It's just taken with the phone?
Yep.
And there's an app on the phone?
No, it's not even an app on a phone, but we put the video through a computer software program.
Ah, okay. Do you know what the software program is called?
This one's called Tumiki. Tumiki.
Tumiki.
Yeah.
Okay. Good Irish.
T-U M-E-K-E, I think.
Sounds Japanese.
I don't know where it came from, but
available for you, or is that a special program that you?
I know my company bought a couple of licenses, so we've got like 2 people that, I take the video, send it off to one of the couple of people that are licensed, and they run through the software program.
Interesting. So is that at your work?
Well, actually, my company has well, what would they call it? It's a volunteer program where we get time, 8 hours to donate, and we could do it during work hours. So in this case, we were at a food bank, as you see, emptying bags of onions into a big tote, and then later some other group would come in later and put it into little bags to distribute.
Great. All right.
Thank you.
Thank you.
Next, by chance, Bob Lewis talking about some chemistry demonstrations. Chemistry. Woo-hoo. Got a
Not
good teacher.
chemistry. But otherwise, fine.
Other than that,
Other than that, it's fine, yeah.
you probably need to either speak into the microphone,
Oh,
or
yeah.
we
Or
could
do you-
give you,
If I
We-
can't project into this room, I should probably be fired.
no, but we're sending things
I
to,
realize that.
It's a video. The video people won't be able to hear you without a microphone.
Okay.
I thought everything was chemistry, Bob.
Here, can I put,
Okay.
are you going to spend most of your time here?
The pan is you?
All right, I'll set this
Oh, this is
microphone
it, yeah.
down on this
Bob,
one.
you don't have a PowerPoint along with yours, do you? Do you have a PowerPoint along with? Yeah. Okay, just wanted to make sure. Just letting the people in back know.
I retired from teaching.
So you got ice and just regular water.
Yeah.
Okay.
That's close enough.
There's one more there, Joanne. Free flowing ice. Free range ice there.
I think these are boiling.
So you've got
All right,
water.
here's what we're gonna do, or what I'm gonna do. Air pressure is kind of an interesting thing. We don't really think about it very much. It's all around us, all the time. We never really think about what kind of force is associated with it. But there are ways to illustrate it. In chemistry, I guess this would be gas laws, but frankly, that's physics. It's not chemistry. In gas laws, we talk about the properties of gases. That's chemistry. The gas laws themselves are physics, Boyle's and Charles and, well, Chuck, for those of us doing well, and Bernoulli and all the rest of those cool laws. But I hope these are boiling. I can hardly tell, but we will find out. I've got some more water inside one of these pop cans. In fact, inside all 3 of them. And hopefully it's boiling at this point. And I'm going to pick it up and flip it over into the pie pan there with some ice water in it, and we'll see what happens. And if it's not boiling, that's what happens. Nothing. So I will take it off and drop it on the floor, because that's what
That's why you had 3.
works well. Try again. Yeah, I know. Told you I didn't want to do this. Okay. Sorry about that. The water needs to boil, yeah.
How about
That's hot, but it's not, they're not boiling.
You want to go to someone else and then we can come back to your...
Actually, I did this at home in the kitchen, and it only took a couple of seconds
Oh, okay.
to get it up to boiling. So I'll ramble for a while.
So you only put a little bit of water in those cans, so
I really told you. All right. Instead, I will wait for that to boil, and while I'm waiting for it, I'll do a different one. And I might be able to pull this off without too much trouble.
Trouble's all right.
I taught for 34 years. I was lucky enough to teach at the high school I went to, Downers Grove North. For the first 10 years that I taught, I was a very, very terrible teacher. I had no idea what I was doing. I went through teacher education in the 1960s, and you've heard that old saw about if you can't do, teach. Well, there's a corollary to that. If you can't teach, teach teachers. And the education program that I worked through really prepared me to do nothing. And when I first went into the classroom, the school I went to taught me to do nothing because they handed me a textbook and a key to the classroom. And they said, go teach. And then 120 kids wandered in at some point, and I attempted to teach. My first year of teaching, I learned probably exponentially more than any kid in the classroom. I also accomplished something my first year that I never accomplished again. I finished the textbook. I didn't know enough not to finish it. So I just went through everything as fast as I could, and I learned a great deal. And the kids probably didn't learn much of anything. I'm not quite sure why this is choosing not to boil. But I'm going to set this on the floor back here. And I'm going to try something else. Oh, it's boiling. I had to pick it up to make it boil. And it's
That's Lewis's law.
I'm going to bring the ice water to the can.
There you go.
Bring the mountain to Miami.
Now, the science behind this is relatively simple. Once it's sitting on the hot plate and it is, hand me back the microphone. Science is relatively simple. Once it starts to boil, the can has in it air. You're never going to get all the air out of it, but it also has a fair amount of water vapor inside it. And when I flip it over in the ice water, the water vapor condenses. So we've reduced the amount of gas that's inside the can. And so there's still a little bit of air left in there, but that amount of air is pretty small compared to the amount of air on the outside of the can. The pressure from the air on the outside of the can is sufficient at that point to crush the can. As I told Carolyn, if I were really doing this in my normal way, I would have bought Orange Crush. And if I was really, really, really trying hard, I would have used Grape Crush, and I would have put a little food coloring in it so that when I put it down in here and it crushed, the water inside the pan turned blue, and then I would have, of course, commented, well, you know what you get when you crush grapes.
Ah,
Wine.
yeah.
You know, it's just, that goes over just about as well in my classroom. It just flies to the end, it hits the wall, and goes out. I do have another one. I don't know if you want to do 5 minutes more.
Sure.
All right.
Why doesn't the can fill with water rather than getting crushed?
The what now?
Why doesn't the can suck the water into it rather than getting crushed?
It's too fast. The hole isn't big enough. You know, I've done this with a 55-gallon drum. Put it on a camp stove, heat it up, and then close the top on it, and it takes about 20 minutes. But the 55-gallon drum eventually goes, and if you look on YouTube, you can find pictures or videos of like tanker trucks imploding. because they've closed them up and then they had something inside that was, you know, a vapor that condensed and then the air pressure on the outside crushed the truck. Those are pretty spectacular.
Next year,
All
he'll
right.
do that,
Yeah.
out in the parking lot.
I never had enough money to get a tanker truck to crush. But very quickly,
I can take that out of your way.
if I get that out of the way. All right. I used to do this demonstration, also an air pressure demonstration, but I used to do it with rather expensive karate sticks. And that was always a kind of a challenge to get, and they cost a lot of money. And eventually I discovered I could get these things that work just as well. You know where we get these, of course? Actually, I get mine at yard sales. They're much cheaper there. That one went over. Okay. I'm going to set this thing out at the end. I don't know. Do I want a victim? Do I have a volunteer? I need somebody that has you look perfect. Do you have any experience with martial arts? Oh my God, no, really? Okay. I did this one time with a kid in Aurora at SciTech. And I asked him the same question. He came up and said, do you know martial arts? And he says, yeah, I do it all the time. And I was like, oh gosh. And I started to do the demonstration. I said, what I want you to do is I want you to karate chop the end of this stick and break it off. And he walked over before I even got a chance to stop him and threw his foot up and kicked it, broke the board. And I was like, well, there goes a demonstration. Okay. If I don't put anything on top of this or I don't hold it and you karate chop it, what's going to happen? Physics. It's headed out into the audience. And, well, let's see. I think I got it lined up so it won't hit anybody. So it should be okay. But what I am going to do is I am going to put some newspaper on top of it. No, the sports section never works. This is the business section. It creates more interest. Some people take stock in that. I definitely don't. But we will set this out. I'm going to put that on top of this. Now, oh, this is great. The table's wet, so we'll be in good shape here. What I would like you to do is get in a position, I don't know if you're left-handed or right-handed, but whichever side. I want you to karate chop this. We're going to do it on 3, okay? These guys, actually, whenever you feel like it. But not until we get there. Don't do it on 1. Okay, and then we're going to have you karate chop this thing. Break it off. We're going to hope, yeah, look at, we've got somebody that has no confidence because she saw my first demonstration. She's already hiding. She's no fool. The kids in my classroom, whenever I would bring out the explosion shield, they always thought that was great because they thought I might die. But anyhow, we're going to set this thing down. You're going to crop on 3. These guys are going to yell, I love science, at 3. The I love science is a very interesting part to this because actually the sound that comes from the last word, science, does cause a subtle change in the molecular structure of the cellulose down here that makes this even work better. Okay? All right, which hand are you going to use? Okay. By the way, I'm getting out of the way. Okay. All right, so I'm going to put the microphone down for a second because I need to use a couple of hands here. Let me get this nice and smooth. So we're going to do this on 3. You're going to karate chop it. Theoretically, the board is going to break. And
That's so much of that.
okay, 14.7 pounds per square inch pushing down on the newspaper. If I flatten it out and there's no air underneath it, that's actually about 9,000 pounds holding it down. There's no way that this board or your karate chop is going to generate over 9,000 pounds. So it's going to hold it down, just a matter of fact. Again, an example of air pressure. If you walk into a gym and watch the guys move the mats when they're doing gymnastics and stuff like that, they don't just lift them up. They shake them first because they need air under them. Or if you watch them take the mats off the baseball field after a rain delay, they don't just lift them up. They shake them. Now, before I understood this stuff, when I watched them do that, I thought they were shaking the water off. And I suspect they might think that's what they're doing. But really, they're getting air underneath it so that they can lift those things up and pull them off the field. There are lots and lots of air pressure demonstrations. Most of them are fairly simple. This one with the can you can do at home. I mean, it's one that works. It's pretty easy to do. If you've got a nephew or a grandchild or a brother that you don't like, you can get them to do that and they'll flip it over. Okay, that's my 5 minutes and 20.
Thanks, Bob. Very nice. Okay. I thought Chris Knight talking about nuclear mass defect.
So, my quick topic is nuclear mass defect. So, what does that mean exactly? And how does it relate to anything anybody might understand? I don't have a slide, but it'll be pretty simple. So, we're going to talk, the easiest way to talk about this is to consider the simplest helium atom. If you know anything about helium, so there's 2 protons, right? 2 neutrons, right? And they're bound together tightly. And what binds them together? And this is related to that. So, because if you have a positive charge, 2 positive charges want to repel each other. So there is something that's binding the nucleus together. It's called the strong nuclear force. But where mass defect comes in is, I'm going to have to quote a couple numbers, so I'll need my glasses here. In atomic mass units, we've measured the mass of a proton. It's about 1.0727 atomic mass units. And the mass of a neutron is 1.0866 neutrons. So if you multiply the mass of 2 protons plus 2 neutrons and you add it together, you would expect that that is the mass of the helium nucleus. And we can discount, we don't have to consider the mass of the electrons because they're so small. It turns out that's not the case, because when we measure the actual mass of the helium nucleus, it measures, so that total should be 4.0318 AMUs. But the observed mass is actually 4.001. So we've lost somewhere of 0.0303 atomic mass units. Now, what's really interesting is if you take that number, and of course you got to do the correct units, and you plug it into Einstein's famous equation, E equals mc squared, which everybody's heard of. So it's energy equals, mass times velocity of light squared. You plug in that difference in that mass, you get an energy number. That energy number is equivalent to what they call the binding energy, which is the amount of energy that's holding the nucleus together. Yeah, it's a lot. Yeah. Now, of course, it's not always that simple. That's the simple case of a helium atom. Once you get to larger and larger atoms, because the strong nuclear force is also dependent upon distance, the larger the atom, the less effect it has on each other as they all interact. So it's not as simple as just saying how many neutrons, how many protons, that's the binding force. So, and of course my wife's going to ask a question.
That's how we make neutrons.
Yeah. And that's where the energy comes from fusion, for example. When you take and if you have enough power to force the 2 protons together, the release of energy is because when they're combined, they actually release energy, and that amount is the binding energy. Or, yeah.
So you're saying that the basic helium atom or nucleus proves Einstein E equals mc squared?
I could say the only thing I'll say, is I'm not a
Theoretically.
physicist, is the experimental measurements that we've made with that theorem seem to prove it, yeah. So, that's all I had. So now you know what nuclear mass defect is.
Thank you. Next year, I plan on giving a whole talk about energy gaps like that. So, great introduction to the topic.
Okay, Carrie? She has a PowerPoint, Dave? I think this is a talk about the science of your brain on art. I'm just guessing.
That's
We
right.
haven't communicated much.
Yes, it is. So I used to be a K-12 art teacher years ago, and now I'm a professor of art and design education at NIU. And as a result, I'm interested in your brain on art. I've done quite a bit of reading about this over the years, but there was a new book that came out called Your Brain on Art just last year. And so it kind of renewed my interest, and I wanted to look into the newer research on the topic. There's also quite a bit of work being done in the health sciences at the moment having to do with art. And one of the things that's being done, in fact, 2 of my doctoral students are doing research on this right now, is the use of visual journaling. So what I've done is included some pictures in here by one of my doctoral students who's doing that research. So I just threw those in for you so you could enjoy some art while you're listening. The thing about the thing about this research, which I want everyone to know, 2 things. One, artists have known this for a really long time, centuries, but they didn't know the science. I mean, so, it's one of those many things having to do with the human sciences that people have known commonsensically for a long time, and scientists are now explaining why. And the second thing is that the research is, well, I don't think we're ready to make any serious, definite conclusions yet. The art community is, but scientists, as they often do, say more research is needed. And we don't, it's like medicine. We don't know what the bad side effects are yet, right?
There's bad
Which-
side effects of art?
Yeah, which is actually true, because there's been a lot of research with children on looking at violent comics and that sort of thing. So we actually do know more than the neuroaesthetics people are claiming, because what they're doing is typically using fine art, and they're typically using art that is valued historically because it's considered, beautiful. I mean, that's one of the criteria. So there's still a lot more work that needs to be done. I've only got like 3 slides,
You
I
got the
think.
clicker right there beside you.
Clicker?
Yep.
Okay. Which button do I push? Okay. There we go. Okay. So, okay, so I can't see the back, so I'm going to try to read from this. So, neuroaesthetics is considered by a lot of scientists to be a subfield of cognitive neuroscience, although it's actually, a child of several other types of scientific studies of aesthetics, like psychobiological aesthetics, which was been around a long time. So this is where it's currently classified in universities, but there are predecessors coming from various sources. It's basically the study of biological mechanisms, but specifically the neural consequences of aesthetic experience, which is what's new in the research. I mean, specifically focusing on neural impact of mostly viewing art. Not enough research is being done on this at all, unfortunately, but particularly not enough research is being done on the creation of art. Right now it's mostly on viewing art, which is interesting because one of the biggest growth fields right now having to do with aesthetics is health science research. And so there is more money being poured into that just in the last 5 to 10 years. And One thing that they're particularly interested in is the effects on, that should be, on the prefrontal cortex and the limbic system, so the, sort of the thinking systems and the emotional systems. I'm giving you all butterflies, so, it'll make you feel good. So the recent results having to do with brain activation specifically is that looking at the art, the type of art I've talked about before, not violent comics, for example, is activates sensory motor areas of the brain. It activates the reward centers of the brain. So when people look at fine art, they have the same feeling that they look when they look at a loved one. So that it acts as a reward to you. And also the core emotional centers, which are, you would guess that, but there's evidence of it now. Let's go, there we go. All right, so what are the physical responses we get when viewing art? This is one of the things I said, people in the fine arts have known for centuries. They've described it, Michelangelo wrote about it. Da Vinci wrote about it, so it's not that we don't know what happens, it's just that scientists are hopefully going to explain why, having to do with how the brain and the body works. So one thing that occurs is we have lower heart rates and lower blood pressure. This is one of the reasons working in the arts, particularly visual art, is being used in the healthcare system now. There are chemical and hormonal reactions. For example, it releases dopamine. What's not to love about that? So it releases not only dopamine, but some of the other happy chemicals that make us feel good. So we want people, basically addicted to art, because instead of being addicted to something that's going to hurt them, they can get that dopamine from looking at art and making art. It can reduce cortisol, which you probably know is the stress hormone. And it also actually redirects brain patterns, which is very interesting. We've known this also from, teaching and learning art for centuries, but when there was a study done fairly recently that studied brain patterns after people walked around an art museum for an hour, and their critical thinking increased and their empathy increased. So there are some really interesting new things that are just being generated. So I'm really looking forward to see what happens with it. I'm using it in a book. I'm using some of this information in a book that I'm writing right now about art and design education for teachers. So that's my 10 minutes, or however long it was. So, is a question?
Wait, I got the microphone here.
So if there was artwork put into like hospital rooms, that should have a positive effect?
So, I'm sorry, I didn't hear the beginning part.
If artwork was put into hospital rooms,
Yes. The answer is yes. I mean, I don't think the research is conclusive enough for people to spend money on that yet, but it's certainly moving in that direction, and I would love to see it. I don't know, it's costly. I don't know what to say. Maybe there's a dust collecting issue too, I don't know. Yeah.
What test did you use to check the critical thinking changes?
They did two things, a brain pattern test, which I don't understand. I'm sorry, I'm not a scientist myself. But also it had people report. They did a pre and post reporting. So it was two mechanisms.
I'm wondering,
Well, that's why I'm saying it needs more research. Yeah. It's anecdotal, but that's the thing about art. Here's the problem with art, folks. Art reveals tacit knowledge, okay? So tacit knowledge is the knowledge that's unspeakable. It's the knowledge we have about emotion in ourselves. It's very hard to communicate to someone else about emotion. We don't know if they have the same exact emotion we're having if we both say the word love, for example. And it's probably not the case that we do. We can look at the chemical reactions that we call love and so on, but the actual experience is very difficult to describe. And so a lot of knowledge that is revealed in art is tacit and therefore very problematic to study, as you might guess. This is part of art and design education to help people put words to tacit knowledge. It's one of the things we do, you know, teach academic language that is accepted in the academy. This, you know, line means this, you know, curved line results in this. And so, you know, we spend a lot of time trying to put words on in tacit, but you can never fully do it. Hence the phrases like, a picture's worth 1,000 words, which is a very silly phrase, but anyway. So that's the difficulty, and that's why it's very hard to study, because we don't know how much of it is, I don't think even scientists know how much of it is individual. It's going to have to be a lot more people studied.
All right, thank you, thank
Okay.
you. I was wondering a little bit about that. Is it the art, or are we taught at a young age to appreciate art, and so we're taught to have it, make ourselves tone down or get a dopamine release or something like that? You know,
We are hardwired to draw. Everyone's hardwired to draw, you know, to some extent.
and then, in my case, it's then to criticize myself for drawing right after that.
Sociocultural issue, that's not the same thing.
Yeah.
You know, as you know, I'm sure all of the kids draw and write words.
Right, there's just drawing and with crayons, yeah. All right, I wanted to go with George Peck. He's got a PowerPoint, I believe, too, right?
Okay, so I'm going to give a little talk about statistics. And I was told to avoid tangents, but that's difficult. I was thinking about talking about mass corona events, which is what creates aurora, okay? And the big majority of the particles thrown off are helium atoms, ionized helium. And when the ionized helium, because it's charged, enters the magnetosphere through the poles and hits the atmosphere, it scintillates or fluoresces, and you get that display. But there have been historically enormous mass corona events and have caused great damage, and that could happen in the future, so beware of those mass corona events. Anyway, to statistics, oh my goodness. As you may have known, Benjamin Disraeli, famous Prime Minister of England, he said, there are three kinds of lies: lies, damned lies, and statistics. So that's the start. So this is really, so I get my little arrow key here. This is actually, no, that ain't it. Here we go. So this is Marcus Aurelius versus Francis Galton when it comes to statistics. So Marcus Aurelius had said, the opinion of 10,000 men is of no value if none of them know anything about the subject. And Galton believed that to be true also. And there we go. Here's Mr. Galton, famous scientist, English scientist of the 19th century, and the father of much of modern statistics. And he, like Aurelius, thought there was no value in these kind of random guesses of these people. But being a good scientist, he was at a livestock fair in 1906, where they were having a contest to guess the weight of a dressed ox. So here's this enormous pile of meat that people would buy a ticket to make a guess at. So these people are not necessarily have experience in animal husbandry or butchery, but they bought these tickets on a chance to win this prize. So someone, came closest and they won the prize. And Galton recognized an opportunity here. So he was able to purchase the 800 tickets, all these guesses, and then analyze them. And what he ended up finding was that the actual weight of the ox was 1,207 pounds, and the mean guesses of these 800 was 1,197 pounds. So only a few pounds off the actual weight. So he was like, wow, this is amazing. And the idea that resulted from that was called the wisdom of the masses, kind of in contrast to Marcus Aurelius. And this is something that's correlation and causality, and this is one of the things that came out of this. I don't know what those bottom pictures are, but the top ones show you things that are well correlated with the number 1, not so well, terribly, and no correlation whatsoever, where it's a 0. You just kind of get this potato-shaped object of data. But this was one of the important things that he was able to elucidate. And he helped develop the idea of regression theories, correlation and causality. Anyone who's done any statistics, these are familiar topics. And through that, through fancy mathematics of least squareds, we're able to do all kinds of cool stuff with with statistics. And so this is one of them, the normal or standard distribution. My statistic teacher would hate the word of use normal. But what you get here is you can see in a normal distribution, you have these terrible guesses on one side and other terrible guesses on the other side, but they all kind of even out. And you get this nice bell-shaped curve. And one of the things I had noticed, this is some years ago now, but I remember going to like baseball games and sporting events, and you get 20 or 30,000 people singing the national anthem. And what I found was it was remarkable that when you had this many people singing, they were actually on key. As a group, they were on key. Now there was people who were sharp and people who were flat, but they all kind of balance each other out. So as a whole, they were on key. So again, this is this idea that you can regress to the mean, or that if you get enough data, things start looking pretty consistent, is what you end up with. So again, here's some of the things that you can get out of statistics. This idea of correlation and causality, which we use in things like weather forecasting, economics, medicine, statistical process control, which has produced some remarkable results in the fields of engineering and other forms of science. And one of the things you get is this thing called a Monte Carlo analysis, which my son, who's a doctoral candidate in physics, is using right now as we speak on a Sunday morning in Riverside, California. And so this can be a very powerful tool in finding unknown things. So if we go back to January 17th of 1966, there was an event over the Mediterranean called the Palomars crash, where a B-52 was getting refueled and things went badly. The fueling plane crashed, killing all of the members aboard, and the B-52 crashed, killing most of the crew. 3 of them did survive. In the meantime, they lost 4 bombs. Bad thing. Not a good day, right. So they quickly found 3 of them because they landed on the land. However, the 4th one they couldn't find, and they looked, and they looked, and they looked, and they couldn't find this darn bomb. So they hired a guy called John Craven, and he used something called a Bayesian search theory, which is like a Monte Carlo analysis, and was able to say, here's where you need to look for this bomb. And lo and behold, there it is. There's the bomb. So you can see the guys with the hats, they're all happy because they're no longer, asses are no longer in the ringer because they lost their bomb. But I think it's kind of funny, the one guy at the end, he's kind of looking like, what am I doing here? Standing next to this bomb. In any case, this again is an example of the power of statistics, and similar methods have been used, for instance, when they located submarine USS Scorpion, famous case of a lost submarine, as well as the Air France Flight 447, which went down over the Atlantic. So it's not just in tragedies, but those were just some interesting examples, I thought, in the use of statistics. So there we have it. Thank you.
I was wondering, kind of correlating the 2 points that you said about this, but I don't think it would do much good to ask 10,000 people
No.
where they think that bomb was, and then go kind of get the average of that, right?
Right.
But what are the methods that they looked at, like what are the most likely possibilities of trajectory and wind conditions and so on?
Right. So, and you can run these analyses over and over and over and over. And then through that, you can come up with some very good idea of what actually happened. So again, it's using computer modeling, as you suggest, as well as statistical theory to do these kinds. So out from not very good data, you can get very good results.
The book, The Wisdom of Crowds, talks about the necessary criteria for a crowd to be able to make mean finding guesses about a subject. And I won't tell you what they are. You can read the book.
But again, I think Marcus was probably talking about military theory or something, probably not livestock.
Speaking of the livestock, that
was done at a county fair?
Yes, in England, Plymouth, England.
Okay, so-
1906.
A lot of the people that were buying those tickets were probably farmers or in the agricultural business.
Probably. They had some foreknowledge, I would
Right,
guess.
right. So if you had done that same thing in this room, I'm not sure you'd come up with a number so close.
Well, this is, you can talk about selection bias. You know, that's a thing in statistics, of course. And, you know, what is the population you're drawing from? Is it truly a randomly chosen populace? And, yeah,
Every political poll is the same thing.
yeah,
Yeah, what population did you choose from?
yeah.
My father used to say, figures don't lie, but liars figure.
Thank you.
Nice. And Kat Gelder? She has a PowerPoint too, I think, Dave, right?
You're not going to break any yardsticks, are you?
Hope not. Actually, it's funny though. If we get to the slide about hand shapes, there's definitely a karate chop hand shape. That's super cool. I just found this meme online and I thought it was hilarious since I was going to talk about linguistics. This guy sinking a bunch of nails into the edge of the waves on the shore, and the man is humanity. The waves are the inherently indescribable nature of the universe, and the pins are language, or perhaps art, right? I love it. All right, so I press this arrow. Even though it goes left, it goes forward. Use the other, the one that's been used so much. Okay, the one that's worn out, that makes sense. Linguistics does not get a lot of airtime, but it tends to really interest people when we talk about it. So I'm just gonna briefly go over what linguistics is. It's the study of language. It is not the study of communication. Those are two different things. And it is descriptive, which is not the same as prescriptive, which are words we use in linguistics that basically mean linguistics assumes that no language is incorrect. There is language that accomplishes the goal of communication, and there's language that doesn't. And there are no correct speakers and incorrect speakers. There are native speakers, and there are language learners. Sometimes native language learners, sometimes adult language learners who have encountered different difficulties than youth who are learning a language. It is focused on spoken or signed language as a primary source of language and language learning and language use. In highly literate societies like ours, we tend to think of written language when we think about language, and that is a byproduct of language. So sometimes thinking specifically about spoken or signed languages can be harder for our brains to do, so it's a bit of a challenge. And also very important to note in linguistics is a historical bias, because a lot of modern linguistics that we think about, especially in this room, the way we would think about linguistics was created by a bunch of white, upper-class, Western-educated men who, particularly in the 19th century and the earlier 20th century, went to a lot of countries that they were colonizing and learned things about those languages that they thought were inferior to English or French. And that has biased the study of linguistics in ways that we're still sort of uncovering and trying to pull out of the practice of linguistics. There's a huge history of harm to Black, Indigenous, and people of color and marginalized communities in the use of linguistics. And so trying to remember that the way that we speak is not wrong, it's just a different variety of English is really important in studying linguistics. And I mention that because this presentation is biased. You may not notice because you may have a similar bias to me. I am not a trained linguist. I did study linguistics in university and college. I have a degree in psychology with an emphasis on linguistics and neurolinguistics. But I speak Midwestern white English, and there's a lot of Englishes I don't know, and if you happen to know a variety of English or a language, and you have corrections or observations for me, I welcome them. I find languages fascinating and always want to learn more. So, let's talk about categorical perception, which happens a lot for people, and it's a very important phenomenon in psychology. It's the difference between perceiving things along a continuous spectrum and putting things into boxes psychologically, mentally, subconsciously, without realizing it. People do this all the time, and there are some things that we do not do this for. So our perception of color is continuous, even though we have separate words for different colors. That's a whole separate Science Sunday discussion, but our perception of color is continuous. Our perception of many other things is categorical. So that's like, well, I've got an example. Okay, so human emotions. When we are adults, we perceive faces and human emotions categorically. And you might have a difficulty looking at this guy, but on the far left, he's going, and on the far right, he's going. So he's afraid on one end, and he is happy on the other. And if you test a bunch of probably white, middle-aged college students, but actually they have gone and done studies in other countries, other populations, there is a categorical perception of whether this person is afraid or happy. So we can tell that on the graph because you can see how these are not straight lines where people just kind of generally, as we go towards happiness, people are just generally more likely to think he's happy. In fact, right between images 4 and 5, most people are going to instantaneously say, nope, he's happy. This is something that we have to ask ourselves, if you're testing adults, is it because they were born knowing how to do this? Or is it because they've picked it up along the way? There are some things for which we are born knowing them categorically. And there are some things which we learn to perceive categorically. Language contains both of these things. But what do babies know about language when they come into the world? Because they come into the world knowing things, prepared to learn about language from before they're born. And when they are born, they begin their great science experiment. But they come with some skills that help them. There are 800 possible sounds in human languages that we know of, right? This is a section of the International Phonetic Alphabet chart. This is not all of it. This is the sounds that you're more likely to encounter in English, and they are grouped based on the left, that's the motion that we're using when we make this consonant. On the top is the place in the mouth where we're producing the consonant. And then inside of each little rectangle, if there are two, well, whatever's on the left is voiceless, and whatever's on the right is voiced, which means the vocal cords are engaged. If you put your hand onto your throat right here and you say, bat, go for it, bat, you can feel that your throat is vibrating the whole time. If you say, pat, you'll notice that that first part isn't quite, there's not as much voice there. Pat, there's a pause. That's the difference between the B and the P, sort of, in English. So that happens for a ton of sounds. There are sounds that humans use that aren't up here because there's no room. All right, every language uses about 40-ish of those sounds. They might use more than 40, but they distinguish between those sounds. So as an example, in English, we use the P and the B. We use the T and the D. You can see the European bias in selecting these symbols. But we don't use this. You see further to the right, there's the C and the weird-looking J. Yeah, we don't use those in English. Other languages, yes. So we'll get to some more things that we don't use in English later. But how are babies supposed to figure out which ones people use in their language? Because let me tell you, in English, people are using that C and that J sometimes. They mean the K or the G, but they're using the other one because people are lazy. So how are babies supposed to know? In my language, we make this distinction, but those sounds, you could just assume that they're this other sound. American English generally uses about 45. It's just a little note there. Babies have got to pick this up because in English, just as an example, in American English specifically, we have a concept of a phoneme, which is a sound that matters in a language. And when we say "pa" or when we say "pa," both of those can be a P sound, but when we say "ba," that's a B sound. In other languages, those would be 3 different distinct sounds. And American English learning babies have got to learn that these first 2 sounds, those 2 that have a P, that are actually technically different, they have to learn that in English that doesn't matter. They're the same sound. They do also, though, have to learn that the TH, that's what this theta is, right there. It's a very quiet sound. That sound is a distinct sound in our language, but not in others. They have to learn that the F sound is separate from the sound in American English, but not in some forms of British English. Those babies are learning something different. So how do they figure this out? Well, it's because of categorical perception. So babies come into the world ready for a lot of these distinctions. They don't come ready to perceive all 800 categorically, but they come ready to perceive some of them categorically. So if I have a baby and I decide to raise it somewhere where people speak Hindi, it comes prepared for the same distinctions as a baby that comes into a family where people are going to speak American English or American Sign Language or Dutch. The baby will perceive it's called an aspirated B, b, as distinct from b, as distinct from p, as distinct from p. It will hear 4 different sounds. And it will notice when you make a different one. We'll pay attention. Oh, there was a different one. Oh, that was different. But by the time a baby has turned 1, if they are raised in an environment where they are exposed to American English, they will have learned that those last 2 are the same. If you play them a P sound and then an aspirated P sound, they're not going to notice that something different has happened, and they're not going to pay more attention. They're not going to be alerted. If you then play them a B sound, they're like, oh, something changed, something's different. And then if you play them an aspirated B sound, man, I don't know what they're going to do, because when I listen to that sound, I still go, what is that? I notice the difference, but I don't know how to categorize it linguistically, and so I don't know what babies would do. My guess is they would just ignore it. This also happens in signed languages, which are understudied but full and complete languages, just like spoken ones. Sign language phonology is slightly different than spoken language phonology, but it relies similarly on some very basic differences between signs. There are about 160 possible hand shapes in signed languages, and there are about 40 used in American Sign Language. This is just a couple of them. And location is also a part of sign language phonology, meaning what part of the body the hand is at, as well as the orientation of the hand. Is it this way or is it this way? As well as the movement. Some signs don't move. Some signs are repeated twice. Some signs move across the body upward, etc. There are also non-manual features in sign languages, like facial expression, and sometimes those have the same difference as saying p versus b in a word. All right, so how are babies supposed to figure out this continuous language when used is continuous? People produce language all the way along this, but the babies are perceiving it categorically. The same thing happens in sign language. Now, when they're born, babies haven't seen any sign language, but they are ready to learn that this is different from this, is different from this, is different from this. And in South African Sign Language, all of those are used distinctly. In American Sign Language, there's this, there's this, there's this, and this probably would be perceived as this. So when they take a 4-month-old baby and they show them those 4 signs on top, they would be able to notice some differences. But if they've been exposed to signed language over a period of time after I don't know how long, they will eventually start perceiving those categorically. And a baby that's not exposed to spoken language, to signed language, will actually lose the ability to categorically perceive hand shapes because they don't have linguistic value, which I think is fascinating, because to me that says, why do we have this categorical perception? And I think that the answer might be more, why do we have language? Why do we have spoken language? Because we can categorically perceive those sounds. And babies, we think babies need that ability in order to find the differences in all of the sounds that they don't perceive categorically, and in order to then learn all of the other things that they need to learn about language. And that is it.
In case nobody recognized it, I grew up in New York. Been living here about 25 years. And most people, a lot of people tell me that they can still recognize the accent difference. Is that part of that process that you were explaining?
Absolutely, yes. So accents, accents are a really important part of language and language varieties. And so a baby will learn in what context to use what sounds. And a baby in New York, actually in various areas of New York even, will...
Brooklyn is different than Queens.
Exactly. So a baby in Brooklyn and a baby in Queens are learning that you use, for example, a different vowel in certain contexts. And so but our ability to perceive what someone is saying and understand it completely, even though they're using their vowels differently, is one of the superpowers of language. Yes, and there's nothing wrong with your amazing New York accent. We love it.
There's a difference between the north side of Chicago and the south side of Chicago.
Oh, yes. Oh, yes. It's wonderful and fascinating.
I noticed a similar thing when I moved here, because I'm from New England, where the R is not really associated with any language. But when I came here, people kept telling me to go to Gulf Road. And I'm going, Gulf Road? And of course, the town out here is Lombard. And I'm going, what the hell? I'm looking on a map and there's no such thing. Because in Illinois, the letters O and U, the enunciations are swapped. The Gulf of Mexico and Gulf Road are entirely different. And Lombard is Lombard, as in Lombardy. And so I was totally confused, and I still chuckle at the Illinois accent.
That's right. We've all got one, those accents. Okay, yeah.
Kat, I'm just wondering if, well, let me preface this. Okay, so in the visual arts, when young children draw who are autistic,
When young children draw,
okay,
yes.
Their drawings tend to be more representational than a normal child drawing. And the speculative reason for that is that autistic children have no choice but to draw what they see precisely because they can't generalize. That's why they have a weakness in language. So I'm just wondering if you know anything about autistic research having to do with sign language and their ability to understand those symbols.
I don't know a lot about that. I know there is research, a lot of research into children who have autism, and I will say that the research that I have read is actually more about the fact that children with autism struggle with learning language. They think because children with autism, many of them are less interested in human faces than children who aren't. And that actually attention to a human face is incredibly important in learning language early on. I don't know if that answers your question, though, or addresses it. But there probably is research into that.
It's really interesting because so little is known actually about it. And there's a lot of speculation coming from multiple sides, Ron included, that somehow autism is related to the ability to transfer information into symbolic form, both in speaking and drawing and writing and so on. So I was just curious about that. So, okay, so now they're looking at whether, is it interest in faces or their inability to generalize or symbolize from faces?
Yeah, I don't know, and I don't know if it's related to categorical perception because people do perceive faces categorically. That's another thing that is involved in categorical perception. So, there you go, question.
Let's get somebody else. Do I have time for one more question or comment?
Yes.
Can you address, what is it that causes our ability to learn language to shut off? Why is it?
I don't know that we know the answer to that. There are lots of different, like, perfect times to learn things in language, but really up until you're about the age of 12 is when you need to learn a language.
Neural pruning starts happening.
Yes.
A lot in your
Yeah.
early adolescence, and that is implicated in a lot of these.
That makes a lot of sense. There you go.
Right. I think we have to wrap it up.
Yeah, thanks so much for everyone. Special thanks for all the presenters. Thanks for coming here today. These are always a lot of fun, and have a great summer, and we'll be in touch. Make sure if you want to